work. And so we have Carlos Ruiz from Colegio de Matematicas Bourbaki in Mexico. Will tell us about O minimality and deep learning. Carlos, welcome.
Thanks, Ed. Is it good, the volume? Yeah, I think it's working. Also, I'm wondering if the size of my handwriting is it good? Yeah.
It's larger, perhaps.
Yeah, you prefer it larger? Okay, I'll do my best. But if I stop doing it, then it's good if you maybe I did forget. Thanks a lot, Ernesto, Liam, for the invitation. As usual, when I'm here, I'm very happy for being here, but sometimes I also feel that I'm an outsider in the conference. I will talk about the deep learning and O minimality, which is an area in mathematical logic. So it might not be deeply related to the rest of the talks, but I mean, it's morally and technically related to the work that we were doing with Ernesto, trying to understand how mathematical models and how optimization techniques, how these statistical approaches to artificial intelligence could lead to a robust or consistent solution. So, I mean, there's a geometry involved, of course, in the optimization, but there are some other combinatorial technicalities that, in this case, arise from this notion of O minimality. So I will give some definitions about deep learning, some definitions about O minimality, and then I will talk about how those two areas interact and why they are interesting for us. Okay. So if you want to stop me at some point, this. So I divided this talk in three parts, as I said. First, I will say a few words about deep learning. This is perhaps the most successful approach to artificial intelligence through data-driven perspective. Then I will give the definitions of O minimality. Just to be consistent, but first, not to be consistent, to be complete, but perhaps some of you have heard this before. I'll try to give some concrete examples. Then I will talk about the learning theory, which is an area of statistics, an area of probability that tries to explain how good or bad algorithms are to approach a function or to minimize a loss function. And then perhaps the key part, I mean, one of the things that I've mentioned to Ernesto, and that I think it's worth looking at is the Kurzweil-Woyla-Schewitz theory. This is a property that differentiable, but I mean, even weaker definitions of differentiability could have. I'm quite bad at pronouncing this. This is Wo, yeah, here. The first inequality was proved by Woyla-Schewitz, and later Kurzweil generalized it to all minimal structures. I will explain the easiest version of this inequality, perhaps the one originally shown by Woyla-Schewitz, and then I will explain how this could be related to other to the problems in the area. Okay. So deep learning is an area of machine learning that uses some very particular and powerful models called neural networks. So the idea is the following, as in any data-driven approach. Let's say we have some set. This set I will call it S, and so it's small, right? S, and I will assume that this is a family of data points. Let's say you could imagine that this is a vector, and this vector has the characteristics of someone in your sample. It could also be a text. It could be a prompt in ChatGPT. It could be an image. It could be just the characteristic of someone, right? And then what I could be many different things. I mean, from a could be just a class. They could be -1 or +1. For example, if you're worried about images, it could be the photograph of a cat or the photograph of a dog, right? -1 or +1. But I mean, in a forecast or regression like problem, this could also be a real number. For example, how many minutes it takes a product to be delivered from A to B. So of course, xi will have the characteristics both from the product and from the path from A to B. How complicated could be this path? But I mean, in natural language processes like problems, this will be a much more complicated object. So, for example, the answer to a given prompt. So, what ChatGPT gives us back, ChatGPT won't give us just a number for the class. This will give us a text, and I mean, it doesn't matter how many, even if it's a word, it's very difficult to not use a larger interface. We could today work only in the classification setting, this -1 or +1, and things should be okay. Right? So the idea is to use a data set like this one. So let's assume you have an algorithm called this, for now, black or blue box. Let's say this is the algorithm, and out of it, we want to find a mathematical model f, right? And what we want first is that f of xi is as close as possible as yi. Okay, so we want this f to model as good as possible the relation between x and y. Okay, so of course here I am assuming that I have the right answers. Okay, so I have the right prompts, I have the right labels for the images, depending whether the images from a dog or from a cat, etc. Right? This is what is called a supervised setting for machine learning. And I mean, even if, for example, in ChatGPT, you won't assume that you have an answer for all possible prompts, of course. And what you do is something called self-supervised learning, where you will, inside a given text, for example, inside a Wikipedia article, you will use some part of this Wikipedia article as your supervised or as your label. Okay, But I mean, in any optimization process, in any algorithm for deep learning, you will have something as a Wi-Fi. Okay, so it's like you'll never have something purely unsupervised. Okay, for now, we could imagine you always have a label that you're going to use, and of course, I mean, it's obvious that if you have this label, it should be easier to find a good F, right? You have the Wi-Fi, and what can you do? Okay. Okay. So I won't say right now what A is, but A is I mean, I won't say it in detail, but A is what is called gradient descent algorithm. You could also say that you have something a bit more complicated. You have back propagation algorithm to efficiently implement gradient descent. It's a bit more sophisticated because gradient descent won't work in real life. You need something called stochastic gradient descent, which makes life easier for computers. I will say a bit. I will say something about this later. Okay. But what I will say something about is F, right? So F will be neural network. When I say neural network, today I will just give definitions of two kinds of neural networks. The neural networks which are called dense neural networks, and the ones called recurrent neural networks. Most of the things that I will say were perfectly fine with a bit more complicated neural networks, convolutional networks, even attention layers, but I won't say anything about them right now. Okay, so when you fix a neural network, you are fixing the parameters of these neural networks, and beta will always be the parameters of our neural networks, and those parameters are the vectors or the tensors in general, which this algorithm will try to optimize. Okay, so you normally say those are the learnable parameters during the training process of the neural network. Okay, so our neural networks are functioning, and the family of possible neural networks with a given architecture will be this capital F. But this means that inside this capital F, I'm allowing to choose different betas, provided, for example, that the length of the neural network is fixed, the number of layers is fixed. I won't go into the details of this, but I mean, the only thing that I'm saying here is that we have a family, and this family is characterized by beta, and beta will live in some fixed dimension. Okay. In general, the big problem here is that this small n is not small, right? So ChatGPT it's trillions of coordinates, but in a very modest neural network, this n is millions, right? I mean, I'm not talking about the $1 million model. I'm talking about any modest neural network will need millions of parameters. Well, and then what I mean, what's the difference between dense and recurrent is just how each layer in this model is computed. Okay, so dense layers are very easy to understand. So let's say that I have a neural network with only one layer, and I will assume this neural network is is dense. So f of x, so this f of x, I already said, it's my bet or my prediction to the characteristics of x. And in this case, you just need to draw. It's a nonlinear function. Okay. So let's say rho is a nonlinear function, and then I probably said this over x. If you remember, it's a vector between v. Okay, so the first thing that I'm going to do is I'm going to multiply x with beta, and beta will be a matrix that has how many output layers. I choose m. Good. So m times v. Okay. So what I'm doing is just I'm getting a vector in Rm here. So this is just so if you think about if you have in mind a linear regression, for example, what we're doing is we're doing m linear regression, one for each row in this matrix, right? And then you have a vector with n coordinates, and to each of those coordinates, you will apply this real value nonlinear function. Okay. Okay. So those transformations are quite naive because they are like a modular. They give you a modular structure for the kind of functions you could use. For example, we could here add they normally call this bias term. This is just an affine transformation. And the interesting part here is that we could continue iterating this process, right? So we have this dense layer, we could then multiply this vector with a matrix this. Okay, and here we could go to some affine or Euclidean space m prime. Okay, and we could add also to this bias, and we could use a different activation function, and then this new function is much more complicated than the initial one, right? Okay. So the number of layers in a neural network first gives you the quality of the approximation to other kind of functions. It turns out that neural networks are there is a, like in the polynomial case, there is a good approximation result saying that any reasonable function is approximated by some neural network. Okay. Which is what we expect, right? But those theorems are void in the practical use of neural networks, because they don't give you anything about how many examples do you need, meaning how large your data set should be in order to approximate unknown relation between x and y. First, I mean that's probably you could learn to distinguish cats and dogs if you have trillions of images of cats and dogs. This is something reasonable, but modern neural networks, they just need some 1,000, 5,000 images of cats and dogs, and I mean this is what we want to understand, why the empirical number has nothing to do with this theoretical number, for example. So this is one problem. those kinds of approximation results. But there is another problem which is a lot more complicated, and it has something to do with in machine learning literature. It's called overfitting, which is how large the variance in this algorithm could be. And this problem is a very difficult and technical optimization problem. It has to do with the regularity of those parameters, and it's there where those results could be used, and they give you nice theoretical results. Okay, so this is a dense layer. The recurrent layer is not too complicated. You just need to do these, let's say, R times, where R is the length of your recurrency. And if you fix this, then you could use let's say, this is your example, right? This is those are the characteristics of your text, of your prompt, or whatever you have. And sometimes there is a sequential ordering in your data, right? So sometimes you want to partition this vector as the first characteristics, for example, the characteristics of the first word that your prompt has, and then you could have the second word. So this is concatenation of the vector. And then you could also have, let's say, k possible words inside your prompt. Okay, so from the point of view of how complicated F could be, this kind of input is very difficult, because it's like a dynamical system. Your beta, you will iterate it, and you could have inputs of arbitrary length. Of course, the parameters are fixed, but the inputs are arbitrary length. So the dynamics of this iteration could be as complicated as you could imagine. And of course, the family of functions used to do this approximation could be very complicated, right? Okay. So I don't know if there is any question about this basic idea of deep learning.
Yeah, but in overfitting, indeed, it's, if I'm understanding correctly, overfitting is in the eye of the beholder in that you have to have kind of a hypothesis of how regular you expect your solution to be.
Yeah.
So that the result is forcing you to see whether this is a bit too much or not.
Yeah.
In C0, there is less overfitting than in C infinity.
Yeah, of course. Yeah. And I mean, and the idea is that in the omni-infinity world, there is much less overfitting, because you're working with very regular functions. Okay.
And just to be sure, this beta parameter has something to do with this a posteriori probability that appears on Bayesian model or something like that.
I mean, in a Bayesian model, you add some prior to your beta, right? So for example, if you are doing this rich regularization or something like this, you assume as a prior that this is Gaussian centered in zero. So I mean, of course, in the Bayesian viewpoint of the optimization technique, you will add this prior, and through Bayes' theorem, this prior together with the likelihood of your data set. So the likelihood is in S, is the data set, and the prior is some in principle arbitrary hypothesis, and then your posterior is what you get through bias theorem and some keep sampling or something like this, right? Yeah, but in general, if you're not assuming any kind of regularization or extra prior hypothesis, then beta is anything, right? It's just any vector or any tensor in this space which is large enough.
But based on the answer, for instance, when you look for this y, I, and then the dissimilarity between this and your f, then you could decide whether your beta is a good parameter or not.
Yeah.
And this can be enforced in the sense of probabilities, for instance.
Yeah. Okay, good. So I will now give a quick definition of an all-minimal structure. This is something that I know I've done many times, but we need to do it. So suppose that you have a family of n. So this is a family of sets in Rn. Okay, so this family of sets inside Rn is O minimal if the following properties are satisfied. First of all, I need this family of sets to be a finite Boolean algebra. Okay. So, for example, the finite union or finite intersection elements here should also be an element here. Remember, I'm fixing n. Well, I'm not fixing n. I'm fixing n, but n is arbitrary. And this property is the one that one would require for a definable set, in the sense that if I can define a set through this formula, and I can define another set through this other formula, then the conjunction of those two formulas should still be definable sets. Okay? The negation of the formula should still give rise to definable sets. Then you have things like the diagonals of x prime are times n, such that those are equal. This diagonal should live inside this family. So this is just adding the quality symbol to your language. Some other technicalities. If you have a definable set in Rn, then this times Rn is also a definable set here, right?
So this is, just let me understand, this is and or equal for all, or what?
No, for all is the fourth property, is the projection. No, this one is just that you can look at it. You can form, you could find infinitely many free variables.
Okay.
You have access to infinitely many free variables.
Now you're going to do the exist.
Yeah, now I'm going to do the resist. And since this is important, here, so let's say you have a definable set inside of n plus m. Okay. And let's say that you have a projection n. So I'm just forgetting the last m coordinates here. Then there exists symbol in your language tells you that this is also definable set. Okay, so meaning that if there exists n coordinates at the end that are part of a first order formula, then the projection is also a definable set. Okay.
So this is a model for this language.
So, yeah, what I'm doing here is I'm describing the family of definable functions, definable sets inside first order.
But is this just a model for the language you're describing, or?
Well, I mean, the thing is that you normally say a model for the theory. So you fix a language, then using this language, you could fix a theory. This theory has a family of axioms, and then you could ask which sets, which structures are models for this given theory.
But
right?
this can be phrased in that sense or
So what I would say is that the language defined by those sets is describing the theory inside this structure. Yeah. Okay. So and this property, what this property is telling us is that the family of definable sets could be complicated, right? But if the theory, if this family of definable sets has these variant problems, okay, this makes things complicated. This hypothesis will also make these things complicated. Here is the graph of the plus function and the graph of the multiplication are elements inside the definable sets in R3. So the graphs literally mean the elements x, y, and x plus y, and the elements x, y, and x times y. Okay, so I add them to make those structures meaningful, right? Because if you don't have addition and multiplication, then the topology induced is not, right? But those hypotheses are to make it less trivial, and then this last hypothesis is telling you that you won't allow definable sets which are too big. So if you have a definable set here in O1, and a definable set over the real line, then A should be almost trivial, right? So A should be either a finite William combination of real numbers or finite William combination of open intervals. Okay, and this is far from being obvious because you have this property, right? So you have very complicated things living here in R and one, and in principle you have many complicated things. Okay, and then what I'm saying is that if you send this A into R, so the first property is telling you that this should be A, right? Well, this should be defined, sorry, and this last property is telling you that it's 10, not just part of this algebraic structure, but it's also very simple. Okay, so I mean, this is the definition of all minimal.
Here you introduce the symbol less than and let it for all the minimum.
Yeah, exactly. So here I'm introducing this minimal order.
This order.
Yeah. Okay. Do you have any question?
I have one question that perhaps is very absurd.
No.
Yes, because you are applying the end, right? Yeah, so for a given construction, is there a maximal
No.
that you
No. That's very important. First order construction should be something over all Cartesian products. Over all Cartesian products. This is fundamental. Okay. To give you a hint on this, you know that Zariski topology over Zariski topology in an algebraic variety won't give you the isomorphism class of an algebraic variety, right? So the topology won't give you anything. But I mean, the interesting results are that in some cases, when you have the Zariski topology, not just on your algebraic, right, but over all Cartesian products, and there, I mean, not the product topology. The heuristic topology induced on tensor products over the variety. Then these full topological spaces will, in the best possible scenario, reconstruct the isomorphism class of your algorithm. So of course, you need this.
And there is no hope with the analytic topology.
Yeah.
So this looks a little bit more like the Zariski case.
Yeah. But there are some results on by college, I think the very recent results where he proves exactly the kind of statement that I'm telling. There is a Bourbaki thing, like 3 years ago, where they talk about those results. Now they're very nice. Okay. So now this result, which is not theorem, but it's a theorem, that tells me that all useful neural networks over are all minimum instruction. This is not a theorem, just because this is not mathematics, right? But if you give me a family of neural networks, say I just allow you to use random functions or sigmoid functions, and I won't allow you to use neural networks with more than black parameters, then this is a theorem. Okay. So all neural networks that I know, either recurrent or dense neural networks, are definable inside an all minimum, a known all minimum structure. Okay. First thing, we're talking about a very famous all minimum structure, which includes not just semiconductor breaks. Okay. And I mean, it's not good to say this, right? But I think this is not a conjecture or something like this. It's just that you need to give me which neural network we are talking about, but then these are very simple results. Okay. For example,
the fact that the sigmoid.
Yeah, you have the sigmoid function and you got the local analytic functions, so everything works fine. Yeah.
Just let me think it for one more side. Like for instance, you are doing this useful neural network, and you need the all the Cartesian products. So in the point of view of like building an algorithm in practice, you have to use like from the computational point of view some variation when you allocate the space to, because you can, like you said that you do not have a model for $1 million, right? You have some finite extension for your memory, right?
No, but the thing is that all neural networks have finitely many parameters. This could be very large. But this is good for first order language because you could just write a very large first order formula where your function is defined. Yeah.
But you can always debate in a finite.
Yeah, always in a finite, because a neural network is a function that you could express using finitely many sequences in your formulas. Remember that whenever you have something f of x, of course this is a free parameter, right? But you allow free parameters in first order. So those functions are finite article. Yeah, it's not a big problem. Okay, well, the question is it important that neural networks are definable in some are unexpected? Well, there is a very nice result, which is the fundamental theory of learning theory that tells you that those functions being definable, it's important for the theoretical understanding of those algorithms that I was mentioning. Okay, I will say at the very end something about the algorithm, but the theorem tells you something. It is a very complicated theorem, and it's something that we've discussed a lot with Ernesto. So let me try to state it in the more minimalistic viewpoint. Okay, so remember, f is my class of functions, and I will allow beta to be the learnable parameters. So if f is non is a family, sorry, the family of neural networks with fixed beta, the learnable parameters. Okay. So I fix an architecture, I fix which layers I'm going to use, which activation functions, and so on. But in this is a fixed neural network. No, this is not with fixed bit. So this is with variable bit. Each function there changes.
It's according for our module space.
Yeah, exactly.
That could be stacked.
I hope not. Yes. But I mean, this variable. Okay. This result is I'm using the fact that those this family of neural network is definable in an only measure, right? So what I'm using here is that this is definable in an only measure. Otherwise, I won't have this. Okay. Then there is an algorithm, an algorithm that has as an input a data set, and then this will give you a trained neural network. Then there is an algorithm such that for every epsilon, for any delta, positive small numbers, and for any v distribution over x times y. Remember that f is a family of functions going from the characteristics of your samples into some output space.
But D is really D is this mind of law.
Right. V is the law that relates x and y, and D is also the probability that you find this example, the probability that you are asked this prompt, or the probability that you find white pixel inside a family of images. Right. So this is
D is the oracle.
D is the oracle. Yeah. So for any distribution, the okay. So something else. I need to say something else. So I will define the loss function with respect to x and y. The loss function of my bet, my prediction. right? So this could be 1 or 0 if y is different to my prediction, then I mean I'm doing a mistake or I'm not doing a mistake, and then I can say how large my mistake is. I have a regression. I can say how large my mistake was. For example, if I ask, if ChatGPT asks answers or something ridiculous, then this loss function should be large. Okay. So then, probability of the loss function of this algorithm with respect to the distribution, of course, this loss function to be as small as possible is as good as you want, provided the difficult part, provided that S has large enough elements. Right. So what I'm saying is that if I have these many examples inside my data set, the family of neural networks could be learned through an algorithm that will have an error, a mistake, as small as I want, maybe not all the time, yeah, but many times. Okay, so this is the learning bound.
It's learning.
So what I'm saying is that this family is learnable, it's tame, and hence it's learned.
But this doesn't go in the other way because then you're overfitting the system with so much data.
Well, the thing is that this loss function is not over your training set, right? Because this probability is over
XY.
non-known examples, right? So of course, I understand if I write here the loss function inside my data set, it's overfitting, right? Because then I'm just saying I am approximating well enough my y inside my S, inside my data set. But this probability, I mean, this is an expected value. It's over new. This is over the test.
But this is going to give us better than path, or what is going to give
No,
us?
this is the fact.
The path.
I mean, path inequality is a lower bound for this.
But this is, we're going not to get better than path here.
So for all neural networks, this n, and this is the last part of the segment, this n is similar to the number of parameters of the neural network. Right? Number of parameters in the neural network is 3. So is the n, is the small n.
That's already very, very cheap because X could be enormous.
No, I understand, but I mean,
But it's not what we're seeing.
no, because we're saying that 1 million parameters neural network is not trained with more than 5,000, 10,000 examples.
So is this proof construction somehow like
This proof,
you give the receipt to the algorithm or something like
yeah, I mean, the algorithm is
not too bad.
It's the stochastic algorithm.
because it reminds me a bit about central games theories.
But this is much better than the central.
Yeah.
There is no hope in the central. But I think it's not what we're seeing. It's what this is infinitely worse than what we're seeing.
No, you're right. This is a sophisticated version of the law of large numbers.
Yeah.
The way you prove this is through Hopding's inequality, right? Which is
Yeah, but what I'm saying is that just apply the central limit theorem is infinitely worse than this.
no, I agree. You need a Hopding's inequality but it's in the spirit of the central of the lower population.
It's just that I wonder if perhaps if you could write out this omnimality just with some validation to make a alphabet somehow and then decouple your results.
No, there are, if we want to agree, it's a bit more complicated. You need the things of the omnimality. So this is called the Rademacher inequalities. But I mean, it's in the same spirit as the central, as the lower large numbers, and the algorithm that you use is a stochastic gradient for this. It's not an unknown algorithm. It's gradient descent, stochastic gradient descent, and you could use backpropagation, but you won't get anything better in terms of statistics. You might get something a bit better using backpropagation in the rate of convergence.
Right. Yeah, the rate, yeah, the speed.
But I mean,
So that's, yeah.
That's nice.
okay. Well, I mean, this is good, but still is not what we're seeing. It's far from what we are actually seeing, right? Okay. Do you have any questions? No. Quick as possible. Okay, so this result, as you said, it's a probabilistic theorem to understand neural networks, right? The problem, I mean, I already mentioned, right? But how do you train neural networks? So you start with some beta, let's say 0, and then you define stochastic gradient descent through this formula. So let's assume you know which parameters you have in the t iteration, and then you will add this the gradient of the loss function over your data set, over a batch, if you're doing stochastic gradient descent, or in this. So you're evaluating the loss function using the previous parameter. So this is the formula of Cauchy method of gradient, right? I mean, you just move into the direction where the derivative is decreasing. Okay? Yeah. So the problem is that even when let's start with some data set, and you start iterating your parameters. In practice, you will normally see some regularity between this and this. Okay. I mean, I'm not saying that this is always true, but this shouldn't be too far away from this, because you want this to be stable, right? You don't want that if you change one element in your data set, then the whole parameter will change, right? Because this will mean overfitting. This will mean that only one element in your data set is being used. Okay, so you want some regularity here. Okay. So those results will never give you the regularity. They will give you a limit theorem. So it's a convergence in law, right? You want a regularity like some convergence in a strong sense. Okay. So thing is that these kind of inequalities, and give you a very concrete statement of this inequality, but these kind of inequalities have been proved for any O minimal structure, right? Not just semi-algebraic sets. He first proved for semi-algebraic sets, then for sub-analytic sets, and those inequalities are quite strong. He later showed those inequalities for any O minimal function, which is quite strong. But a generalized version of those inequalities will give you a regularity on the convergence of those parameters, right? And those are two of the results that have been proved in the last year using generalizations of those inequalities. I mean, this is.
Do they cite this work by Gromov? Do you remember?
Oh, maybe they won't, but those were the same ideas, right? The ideas by Gordon Schultz are Gromov's rich ideas. You mean the ultra limits of
Yeah, because that's the spirit of it.
yeah, that's the spirit. Okay, so just to give a definition of this KL property. So you say, I mean, here I stated in a more general setting, but I will try to do it in just one variable for it to be as transparent as possible, right? So let's say that you have this function, continuous function, open set, and let's assume that this function has a unique point, unique minimum point first. Minimum at 0, right? Then f has the KL property if there is some function, say C, this function should go from 0 R, and this function should, this is important. F should be O minimal function, right? Findable in some O minimal structure, then there should be a phi function, and this phi function will be some kind of desingularization of F, right? So this function is definable. This function is C1. This function here. This function is here. Yeah. And such that if we are here less than R, or to finish there. So then the Euclidean norm of phi f(x) is larger than 1, provided that f(x) is larger than R, right? So what I'm saying here is that maybe f is not very simple around 0. So we know that at 0 is minimal, but maybe f is not very simple. Maybe it's not convex. Maybe it's not smooth enough, or something like this. But if it's O minimal, then we can reparameterize at least the gradient of this function to make it bounded, right? Okay. This is a very weak version. A stronger version is the one that I had in mind, and is the one that you will find in those two papers. I presented those two papers to Ernesto, they are very recent, and they use stronger versions of this inequality to prove something meaningful about the regularity of the betas. And this, I believe, it's a powerful tool to understand these comparisons, but many other things. I think that there are analytic questions, like deep analytic questions, that could be understood through this Tame properties. Thank you.